Hey AP Chemsters, this is Mrs. Vanderwall bringing you the last installment of section 13.4 of the Blackwell series. I would like to once again emphasize that if I say to pause and work out the problem yourself, really do that. I try to leave little spaces so that you can pause, work things out, come back and see how you do. So I highly recommend that. So problem 16, we're talking about butadiene reacts to form its dimer according to the equation. There you go. They gave you a couple graphs and they gave you the data. So it says according to the following graph. So we're looking at these two. Is the reaction zero, first, or second order? Well, if it were zero order, they would have given you the concentration versus time graph, but they obviously didn't do that, so it's not zero order. So over here, we're looking at the natural log of the concentration there, and that is consistent with a first order reaction. But now look at the graph. Is this linear? No, it's not. All right, so you cannot use y equals mx plus b like we did, in the prior problems with this graph. It is not linear, so if it's not linear, it is not first order. So what about the second order? Well, they gave you 1 over the concentration, which is consistent with second order. And is this graph linear? Yes, it is. So this indeed then becomes, it's a second order equation. So let me just kind of circle that. This is a second order. All right, so let's see what they ask for next. So what is the value of the rate constant for this reaction? Okay, well, it is second order. So what is the equation that you use to find the rate constant of a second order equation? You're given time, you're given concentration. Hopefully you figured out, oh, I need to use this equation. And you're going to solve for K. Y equals mx plus b, we get all the information. So now go back and look up here and decide which one of these values. You can use any of them you want. Save this one. This is a special one at time 0. That is your A0. That's your initial concentration, but go ahead and use any of these. So I'll give you a little bit of time and plug in whichever value you want and see what you get for K, and then we'll compare and see what I got. Okay, so I particularly chose the second value. Hopefully not everyone did that, so we can compare the different K values. So I plugged in, and can I emphasize once again, I sound like a broken record sometimes, write down your units. Very, very important that you do so. Don't be lazy. Write down your units. All right, and then I went ahead and I did the math. Now notice, even though 1 over 0.00625 is 160, notice that the molarity is still in the denominator. Same with over here, 1 over 0.01 is 100, but molarity is still in the denominator. And I guess I was a little bit lazy. I didn't plug in the unit there. Here I did. I subtracted. What's 60 minus 100 is 60, and it's 1 over molarity. And then when you're done, here's your K. So when I divided by 1,000, molarity is in the denominator, so is seconds. And I hope you recognize that this unit, molarity to the negative first and seconds to the negative first, is consistent with a second order equation. If you go back and look at section 13.2, 13.3, you'll see that these are the units that must be there for a second order. First order, it would just be seconds to -1. And this is why I encourage you to write down your units. So let your units guide you. If you got something different than what I got, at least unit-wise, you made a mistake. Go back and figure it out. All right, so about letter C. What is the half-life for this reaction? Pause this, do it on your own. Okay, well, hopefully you came up with this equation. Once again, you're not necessarily going to have to memorize this. It'll be given to you if you need to know it because it's not in your equation sheet. And then I plugged in my values. Okay, so here's the K value I just figured out from here. And then here's my initial condition again. Now notice what happens. Again, this is why units are so very important. Your molarities cancel out. Check that out. So what are you left with? Seconds. Now really, what is this all about? You have 1 over seconds. And so if you're going to rationalize the denominator, think about your algebra skills, you end up with seconds on top. So here is this value, I guess with sig figs, what, I've even forgotten, 3 sig figs? Let me check up here. 3 sig figs. So that should be really 1670 seconds. Okay, so hopefully you got that. Makes sense. Let's check out the next question, problem number 17. All right, I like problem number 17. I think you always need more practice with multiple choice questions. So this one says a decomposition reaction, so it has only one reactant with a rate that is, write this down or underline this, observed to slow down as the reaction proceeds, is found to have a half-life dependent on the initial concentration of the reactant. We need both of those facts to help us out. So which statement is most likely true? At this point, you need to think about, is it 0 first or second? That way we can answer A, B, or C. So pause, think this through, and decide what you come up with. Okay, well, let's check this out. Let's see if we can't figure it out. Zero order. Well, I wrote down the half reaction for the zero order because I'm looking at the second important piece of information. The half-life depends on the initial concentration of the reactant. Well, it does. So what about the first part? Observe to slow down as the reaction proceeds. What does it mean when the reaction proceeds that the concentration of your reactant will typically change? Okay, it's probably going to be used up. So what happens as you used up your reactant? Does it slow down or not? How are we going to answer this? Well, I encourage you to go back to page 5 and look at that graph. Yes, this graph. So what am I looking at? Rate versus concentration. Oh, that's what that question was asking me about. So they're saying as the reaction proceeds, the rate's going to, I forgot, increase or decrease. I think it was or decrease, right? So what's happening here? As A gets lower and lower and lower, what's happening to the rate? Is the rate decreasing? No. It remains the same. That's what zero order is all about, is that the rate doesn't change. It is not dependent on the concentration. So could this be zero order? And your answer is no. Go back to page 16. Okay, so it's not zero order. Okay, what about first order? Well, let's check this out. What is the half-life reaction of a first order equation? Well, here it is. Is it dependent on the initial concentration of A? No, it's not. It's only dependent on K, so it's not first order. So let's hope that it's second order, and here's the half-life of that. Oh, look what I found here. I found it does depend on the initial concentration of A, and so does it slow down as the reaction proceeds? Again, does it slow down as A gets used up? Why don't we go back to page 5 again? Okay, so here's the rate and the concentration again. So as A gets used up, as the amount of A decreases, what's happening to the rate? Is the rate decreasing as well? And the answer is yes, it is. So as A gets lower, the rate gets lower. The converse is also true, but that's not the question's asking me for. So between the half-life equation and this graph, it is a second order. Why don't you go back to page 16 now? All right, so is it A, B, or C? Well, question A says apply the natural log of the concentration of the reactant as a function of time is linear. That's not second order, is it? It's first order. See, look at here, first order, natural log. So A is definitely not correct. What about letter B? A half-life of the reaction increases as the initial concentration increases. Well, let's check this out. Let's go over here again. It's second order. So they're saying as this goes up, that this goes up. Does that make sense? Well, let's check it out. What happens if you increase the denominator? Does this number also get bigger? No, this number is going to get smaller. So B is wrong. All right, so this would be correct if it read the half-life reaction will increase as the initial concentration decreases or vice versa. So B is incorrect. So let's hope that letter C is correct. The doubling of the initial concentration of the reactant results in the quadrupling of the rate. And that is true. If you go back and look at page 5, which I'm not going to do, you'll see that is correct. And this really is the classic definition of a second order reaction. So let's go on to letter or problem number 18. All right, so this is the integrated rate laws for reactions with more than one reactant. Once again, we've been talking about just decomposition. What about all the others? There are many different kinds of reactions out there that are not decomposition. How do we deal with those? Well, you need to do this experimentally, and you need to contrive or make the experiment so that you have large concentrations of all the reactants but one. And from doing that, you can determine what is called the pseudo order rate law. So whatever that lowest concentration one is will then determine the rate law of the entire reaction. So it says examine the rate with one reactant very low. I don't know why I have question marks here, concentration, and the other one's much higher. And so here in my example, I have 3 reactants in the order of X, Y, and Z. And again, they're saying if A is the one with much lower concentration than B, then your pseudo rate order all depends on what the order of A is. So A could be first, second, or 0. So let's look at problem number 18. And for me, problem 18 really clarifies what this is all about. So consider this hypothetical reaction where the rate is equal to Ka(B) squared. So what order is it in A? It's first order. We left the exponent out because it's a 1. Where'd C go? Well, C must be a 0 order because C to the 0 power is 1, so you can just leave that out. And look at the experiment. Which reactant was put in the smallest quantity? And if you look at the initial, you'll see it's A. And then B and C are much larger than A. So the reaction is started after 8 seconds. The concentration of A is 3.8 times 10 to the negative third. So what order is your pseudo reaction going to be? Well, which reactant is in lowest quantity? It's A. So what order? Look over here. What order is A in? It's in the first order. So it says now calculate K for this reaction. Well, what are you going to do? You're going to calculate K assuming first order in A. Okay, so what is that going to equal? You figure it out. Hopefully by now you know first order and natural log go together. So let me just kind of throw these numbers up at you. If you haven't done this already, go ahead and pause this and figure out the rest on your own. Here we go. And so K is equal to 0.1211 over seconds. And once again, notice the unit. This is consistent with a first order reaction, which is true. And then it says calculate the half-life of the experiment. Pause this, figure it out. Okay, hopefully you figured out you needed this equation. Put this here. And I got 5.72 seconds. Folks, this makes a lot of sense to me. And think about this. Hopefully it makes a lot of sense to you. So this is roughly 6-second half-life. So after this reaction is proceeded and 6 seconds later, we should have half of this amount, which is 0.005 molar. Now look at problem number A. 8 seconds is a little bit beyond 6 seconds. This is a little bit more than 1 half-life later. So this number should be a little bit less than 0.005, and it is. Now let's look at number letter C. Calculate the concentration of A after 13 seconds. Why don't you pause this and figure it out yourself. Hopefully this is getting easier for you. You're using the same equation, plugged in the numbers, and I get A is 0.0021. Now, once again, this makes a lot of sense to me. Why? Because this is a little bit more than 2 half-lives later, isn't it? So 2 half-lives later, remember that chart I had you draw earlier? That would be about 0.0025 molar, and this is a little bit more than that, so this should be a little bit less than 0.0025, and it is. Now, I really like question D. To me, this is what really ties this in. How does C relate? Well, C, we're not talking about C, we've been talking about A this whole time. So how do I incorporate C? I do that by setting up my BCA table. So here are my initial concentrations. Notice that this is my concentration I came up with after 13 seconds. So what did I have to do to get that number? I had to subtract this number here. So what will I put in this spot? Well, what's 0.007? I made that rounded to 0.008 times 2 is this. So C is 1.98 molar. I'm running out of time, so let's kind of zip to the next one. Go to page 615, and you can fill this out yourself. I hope this was helpful. You'll be getting some problems later. Have a good day.